Hello, welcome back to another session of chemistry. Okay, today we are going to do some fundamentals based on the history of the atom. Okay, so how this atom, the discovery of an atom began, and what we are supposed to know uh, from uh, from school perspective or from learning perspective. Okay, so it all began long, long back. Okay, so during the 5th century, I would say, uh, Democritus, okay, he coined the name the atomos. So the thought came is what happens when you take a matter and then you try to divide them. So you try to divide the matter into particles, into particles, into particles, make smaller and smaller and smaller. And what happens at the end? So you have to reach a place where it is completely indivisible. Okay, so that's where the idea of an atom, there should be something which you cannot break into two. And then that thought was taken further later on by John Dalton. And then the idea of the the atom, the real atom came. Okay, so the atom, each elements are comprised of what are called as atoms. So if you take any element in the periodic table, hydrogen, lithium, beryllium, whatever it is there, it is the individual particles are called atoms. Okay, these are the tiny particles or the individual units of any element. And all the atoms of the same element will be identical, right? So they will be identical. So hydrogen and hydrogen will be look identical. And if you have compounds are nothing but if you mix two or many elements together, it will become compounds. Okay. And these compounds, the ratio will always be a whole number. Okay. Whole number. So it will not be a fraction. Okay. Not be a fraction. And the discovery prolonged in such a manner that what is a chemical reaction and what happens in a chemical reaction. So in any chemical reaction, an atom cannot be destroyed or created. Okay, you cannot newly create. Okay, so let's say that you have two atoms. This is a compound. XY is a compound, and then reacts with Z, an element. It can interchange and then form Y. So in other words, suddenly in the reaction, the Z cannot disappear. The Z cannot disappear. Okay. So it must be somewhere. Okay? Either it would be as unreactive or it should go with someone. Okay. So, or this XY can dissociate as X plus Y. Or this XY can react with another compound ZA to form interchange itself. Something like this. So that means the whatever it's here must be on this side. Left side must match right side. So they should be there. Something cannot disappear. There are few laws that was came during this discovery process. The first law is the law of definite proportions. You can read all these things in a book, okay? And to understand that's much better, you can watch an animated video or something, okay? Most of the time, they won't ask you all these things in an exam, okay? But it is better to know as a starting of a chemistry class, you must know all these things, what happened in the uh, at the starting of the chemistry class, okay? So it is better that you know this. So different samples of the same compounds, okay? If you take different samples of same compounds. So let's take, you take water from a lake from New Jersey, and you take water from Colorado, you take water from Hawaii, okay? They will have the same proportion, right? Same proportion of constituent elements. Okay? This might look now uh, and same property by mass. This might not look something bizarre, because the thing is, um, there is nothing fancy about this, because you have it anywhere you take that, this will have, the water will be the same, right? It will always have uh, two hydrogens and one oxygen, irrespective, and they have the same property, okay? By mass, they will have hydrogen, and they will always constitute 11.2% and 88.8% by mass. Okay, this is a constant, right? Irrespective. So this we must remember. The second one is the law of multiple proportion. What is law of multiple proportion? So we saw the law of definite proportion. In definite proportions, you see that they will have the same constituent, right? The hydrogen will be 11.2% and oxygen will be only 88.8%, irrespective of any place. Okay. So in multiple proportion, you have, if you take nitrogen that reacts to form two compounds, let's say nitrogen reacts with oxygen to form NO and NO2. So the mass of one element, so this nitrogen that combine with fixed mass of other element, in that case, that's oxygen, will always be a whole number. Once again, it won't be a fraction. Okay? It won't be like NO 3.5 or something. Okay. And the third law is, we have already seen this earlier, is the law of conservation of mass. So whatever is on a reaction, which is on the left side, will be on the right side. Okay, so in a physical change or in a chemical change, right, the matter cannot be destroyed. Okay, the matter is not destroyed, right? So what is a physical change? Physical change means what is the most important thing in understanding physical change? Physical change means no bonds are broken. In chemical change, bonds are broken, right? So when water solid, when it melts to liquid, this is a physical change. When water, liquid, or gas separates into hydrogen gas and oxygen gas, this is a chemical change. So I am breaking the bonds. Clearly, I am breaking this bond. This is a chemical change. Okay? So in either case, I should have equal amounts of whatever it is there. I should have equal amounts on left side and right side. Okay, so that is called as a. In both cases, I should consider as the mass must be conserved. If I have 5 grams, I should have 5 grams of this. If I have 10 grams of this, I should have 10 grams of this. Okay, that is very important. So when you take the in the earlier things, as we say, these are all the initially they talked about elements and then how they reacted to form uh, how the initial process of the atoms combine to form elements combine to form compounds. But the main theory still remained about what is an atom? How does an atom look like? So first, J.J. Thomson did started his research using cathode ray tube, which looks like an old television tube. Okay, so he stated that an atom might look like is comprised of both positive charges and negative charge, but these positive and negative charge might look like a plum pudding. He came with a plum pudding model. So he said the positive charge and negative charge are all scattered inside each atom. And during that time, the radioactivity was also happening, research was also happening deeply on nuclear chemistry. So these times around 1895, Röntgen, Antoine Becquerel, Marie Curie, Röntgen were working on X-rays, and these guys, both of them, were working on the alpha, beta, and the gamma rays. Further, Ernest Rutherford almost 1910, he did the famous gold foil experiment. You have to watch this in a YouTube or something. I will try to add a link here. Gold foil experiment, where he said the number of protons are placed in the dense nucleus. Okay, so this is not the plum pudding model is not an appropriate model. The nucleus is centered and it's dense, and the negative charge electrons is almost going around, and the atom is mostly an empty space. Okay, this is a very important discovery. Okay, this gold foil experiment is a very important discovery. And Chadwick, his student, discovered neutrons. And at that point, we have very clear picture that the atom consists of three important particles. One is proton, and another one is neutron. Both of them are inside the nucleus, and the electrons revolve around. At the same time, or around that time, Bohr came with what is called as the planetary model. The planetary model states that this is almost like 1913 or something. So the question that arises, that why we can remove some of the electrons, but why cannot we remove all the electrons? So there should be levels of electrons. So that is the reason Bohr came with a planetary model in such a manner that the dense nucleus should resemble like the planetary model in which the sun is at the center and the electrons are revolving like planets around. So in other words, both the microcosm, the atom, and the macrocosm, the universe, uh, resemble each other. This is very, very important. Now, what we follow is the quantum model. That is the latest model that we follow. We'll go over this model later, okay, when we go over the electronic configuration. The next one is understanding the light and waves. Okay. The light and waves what is a wave? The wave is nothing but a vibrating disturbance. Okay, anything that vibrates and produces a disturbance is called as a wave. Okay, and it's definitely is going to emit some energy. All waves emit energy. So we have what is called as an electromagnetic radiation. The electromagnetic radiation and the electromagnetic radiation or the electromagnetic spectrum is a wave. And the length and speed of the wave will determine in which part of electromagnetic spectrum it belongs to. Okay, so it can be X-rays, can be radio waves, it can be anything. Okay, so it all depends upon where it is. But to identify, we have a very simple formula that we are going to use. Okay, so mathematically, This is very useful for us. The energy of any wave is represented by its frequency. So the energy is directly proportional to its frequency, called, it's a Greek letter, it's not a V, it's called a mu. Very is equal to frequency. But mu is equal to C by lambda. This is also a Greek letter, lambda. Lambda is the wavelength. So E is equal to h mu, which is equal to hc by lambda, because mu is equal to C lambda. So in this formula, this E is equal to hc lambda. There are 4 parameters here. Energy, h, which is called as the Planck's constant. C, which is the velocity of light. Lambda, which is the wavelength. This is also a constant. Mostly this will be given. If not, you have to memorize this. So out of these 4 parameters, 1, 2, 3, 4. 2 are already constants and you have only 2 of them. So you can easily calculate in terms of mathematically, if an equation, if a question is given, if an energy of a wave is 1.8 into 10 to the power of minus 19 joules, what is the wavelength? That is the question. Then E is equal to hc by lambda. Lambda is equal to hc by E. And then you substitute all these values. Planck's constant, h is equal to 6.626 into 10 to the power of minus 34 joules second. And C is equal to 3.00 into 10 to the power of 8 meter per second. This is given mostly in all the books and in the reference sheet also. So you can use them. So I'm going to write 6.626 into 10 to the power of minus 34 joules second times 3 into 10 to the power of 8 meter per second divided by 1.83. That is what I'm using, into 10 to the power of minus 19 joules. That is the energy. So if I calculate this, the final answer I should end up should be 1.09 into 10 to the power of minus 6 meter. What is the mistake usually students do? That's what we have to worry about here. So you have to know the mistakes. Even the AP kids do the simple mistakes. We know algebraically 10 power x times 10 power y is equal to 10 power x plus y. And 10 power x divided by 10 power y is equal to 10 power x minus y. Okay, so you're going to use a mathematical, you're going to use a calculator. Okay, so you have to know how to use the calculator first. Okay, you have to use how to use the scientific calculator first. Okay, sometimes when you type this in scientific calculator, if you don't know how to use a scientific calculator, then you will get a wrong answer. Okay, you will get 1.09 or something, 10 to the power minus 44 or something. So you should be very, very careful about it. Okay. Yeah. So if you're going to simply mathematically, you're going to do, but you should know how we are going to do this. Right? So if the simple way or easiest way using the scientific calculator, but you should know how to use the calculator. But since the other way to do this is taking these numbers 6.626. Take only the numbers and divide them and get the number. And separately take the powers. 10 point minus 34 into 10 to the power of 8 means plus 8. Minus 19 means when it comes to the top, right, it is going to have minus of minus plus 19. Right? So it is going to come 10 to the power of minus 7. And then you change this into one single digit, right? That's 10 to the power of minus 6. Okay. Your question is asking for the only number given is 1.83. So it has 3 significant digits, 3 sig figures. So your answer must also have 3 significant figures. So this is how you have to solve the problem. Okay. Solving this kind of problems is very important. Okay. So in this light and waves, this is what the most important thing is, revolves once again around only this simple formula of this E is equal to hc by lambda, in which there is only one parameter is given, the other two parameters are constants, and there's only one parameter you have to discover. Okay, so that is very important. Okay, so what are the things about this atom? Once again, you have to initially, for the atom, the discovery, I suggest that you read a book to understand this, but mostly not many questions come from this area, but you should be aware of what are the different laws that defines them. The law of definite proportion, law of multiple proportion, law of conservation of mass, and how the evolvement of atom came into being. Okay, how the atom is consisted of a dense nucleus and the electrons go around, and who are the key contributors in this. Okay, so like Ernest Rutherford, the gold foil experiment is most important. The cathode ray tube is very important. Okay, the cathode ray experiment is very important. The gold foil experiment is very important. And then the Bohr planetary model is very important. You should be aware of this. Okay, and then you have to be aware of the most important formula, how these waves are connected to this, because each and every wave is connected as what we call as, they emit energy in the form of photons called as in pockets of energy. Okay. So we are going to go over this in photoelectric effect later, but initially these are the ones that you have to know. And you have to know that this revolves around a very simple formula, and this formula is how to calculate either from energy to wavelength, or from wavelength to energy, or from frequency to wavelength, and so on. But how to solve them with calculator or without calculator, how to solve them very clearly. In our next class, we are going to look on very, very important concept called as the electronic configuration of elements, where electronic configuration of elements, the electrons, to describe the electronic configuration is written to describe the location of the electrons. Okay, the electrons are nothing but an eye of an atom. Okay, this is very important. These are the eyes of an atom. Okay, so their hydrogen has one proton and one electron. So when a hydrogen is standing next to another hydrogen, it senses that this guy is a hydrogen, this guy is hydrogen, because Each of them sense each other. The electron can see the neighbor has only one electron and one proton. So if it has one electron, one proton, and there's no other charge, that means he is also a hydrogen. So the elements see each other only through a uh, by their eyes. Their eyes are nothing but electrons. So if you take a big a small bowl of water, and then you add a pinch of salt, just a pinch of salt inside, sodium chloride, and then just each and every sodium ion and each and every chloride ion, the water can sense them and they can surround uh, very clearly. They know that this guy has entered into their sea. So there is a reason why I'm drawing this, which will learn, which you will learn eventually. So this is what we are going to learn, this very important key principles of the electrostatic attraction that they encounter on the electronic configuration in future class. Okay. Stay tuned. Please subscribe to the channel. It is very important. I see that many people are not subscribing. Please subscribe channel. That will help us to make quality videos.